Hello everyone, welcome back. So we're going to continue talking about binomial experiments. So if you recall, a binomial experiment is a probability experiment with these conditions. This experiment consists of n independent trials, so they do not affect, one trial does not affect the probability of another. There are two possible outcomes for any trial. We can call the first one a success, and we call the second one a failure. Again, those are just arbitrary labels here, just to keep them distinct. And then we say the probability of success in any trial is always the same. It's always equal to some number p. And then that means the probability of failure in a single trial is also always the same, and that's going to be 1 minus p, or q. And we're interested in the random variable x. It's the number of successes. And we're going to, we say the probability distribution for x is called a binomial distribution. Obviously, since x, there are only finitely many possibilities for x. X can just ranges from 0 to n. So x is a discrete random variable. And because of that, we can compute the probability distribution using some of our counting techniques. So we said that the probability of x successes is given by this formula: n choose x times p to the x times q to the n minus x. Okay, we computed that. We explained why that is in the last video. So now let's see if we can get the entire distribution, and then from there we can answer some other questions. In this next example, we have 56 of U.S. adults say they plan to get the flu shot, and you select 7 U.S. adults at random. And again, we're going to allow the possibility you might select the same person more than once, even though in reality you never would. And then you ask them, are you planning to get a flu shot? And we're going to let X be the number of adults in your sample planning to get the flu shot. All right, so we've got that X in your sample, planning there to get a flu shot. Okay. All right, now what would be the, let's use that formula, and we can say what would be the probability that exactly 3 plan to get a flu shot. Well, that would be the probability that x equals 3, or 3 successes. And then according to our formula up here, that would be 7 choose 3 times. Now, here's the thing. What's the if we define a quote-unquote success as that person saying yes, they're going to get a flu shot, and we just define a failure as them saying no, we're not going to get a flu shot. Okay, then the probability that they say yes, or we can say the probability of yes, would be 0.56, just because we already know it. We're given that 56% of the population are planning to. So the probability that one person says no would be 1 minus 0.56, or 0.44. Okay. Okay, so in this case, the probability that exactly 3 plan to get the flu shot, that would be 7 choose 3 times 0.56 to the third times 0.44 to the fourth. Okay. All right, and that turns out to be 0.230. So we're talking about 23%. Now we can, in the same way, we can get this following distribution here. Here's x, and here's p of x. And here, what are the possibilities for x would be 0, 1, 2, 3, 4, 5, 6, and 7, right? Okay, and I computed this in advance. We already found that our probability when x equals 3 is 0.230. And it turns out the other probabilities where basically you just, instead of 3, you replace 3 with whatever x is and 4 with 7 minus x. For 0, this would be 0.003. For x equals 1, it's 0.028. For x equals 2, it's 0.109. For 4, it's 0.293. For 5, it's 0.224. For 6, it's 0.095. And for 7, it's 0.017. Okay. All right. So there's the probability distribution here, the binomial distribution here. So let's say we modify this question a little bit, saying what's the probability that at least five people plan to get the flu shot? That would be the probability that x equals 5 plus the probability that x equals 6 plus the probability that x equals 7. Okay, and we can just add these together. These are distinct. These are mutually exclusive events, right? X can't be equal 5 and 6 at the same time, right? So we just add these together. And so this would be this number plus this number plus this number. So this would be 0.224 plus 0.095 plus 0.017, which turns out to be 0.336. Okay, and then if we wanted to find the probability that at most two people plan to get the flu shot, well, at most 2. So what are the possibilities for x? Could be 0, 1, or 2. Okay. So this would be the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2. Okay, and so we're talking about these three probabilities here. 0.003 plus 0.028 plus 0.109, which is equal to, I think, 0.14 or 1.140. All right. Okay. So once you actually have the distribution here, it's not too bad. Well, something like this is not too bad. Now, or if you don't have too many numbers to add up. Now, granted, for a lot of these problems, you're going to have more than 7 trials. So we're going to show you in a minute a way to simplify this on your calculator. So, but I do want to define one last thing. Is we talked about the mean and the variance and standard deviation of a random variable, or at least of a discrete random variable. And we had this nice formula, or not a nice formula, but a kind of a complicated formula. But the good news is that we don't have to. It gets very simple when we have a binomial distribution. Okay. With binomial probability distribution for an experiment. The mean just turns out to be n times p, where p is the probability of success and n is the number of trials. The variance is npq, and the standard deviation is the square root of the variance, so it's the square root of npq. So and the mean, again, the mean is kind of like the expected value of x. So what would we expect? What was the theoretical average of x in the long run? So from in the previous example, okay, n was 7, p was 0.56, and q was 0.44. So the mean, which is also the expected value of x, is 7 times 0.56, which is basically 56% of 7 is what we kind of makes sense, right? And this turns out to be 3.92. Okay, so theoretically, and we would expect 3.92 people to get the flu shot, even though it wouldn't make any sense to have exactly 3.92 people in your sample getting a flu shot. The variance would be 7 times 0.56 times 0.44, which is 1.724. And the standard deviation would be the square root of that, which would be approximately 1.313. Okay. So this is a way, kind of a way how the probability distribution is spread out. So one last thing about how do we actually compute this. If you want to find the probability without necessarily using that formula with the with this, so if we wanted to compute what this is, n choose k, with p to the k, q to the n minus k, is there a way we can do this without actually plugging all this stuff in and worry about round off or something like that? Well, the computer can do that with a special command called Binomial PDF. Okay, and I'll just show you how to find that on your TI-83 calculator. So what it does, all you have to input is the number of trials, the probability of a success on each trial, and how many successes you want. So here it is. What you want to do is hit the distribution button, which is right here. In my case, it's above bars. So you hit the yellow button and then distribution. And you want to go all the way down until you see Binomial PDF, which is down here at number 10. You don't want CDF, not yet, but PDF, and enter that. And then in our case, let's see, our n was 7. Our probability of success was 0.56, and let's say we wanted to find it for, let's say, maybe 5 successes. Okay, we enter that, and we get 0.223, which we round off to 0.224. So that's how we do that. We use Binomial PDF to simplify this. Now, if we this tells you that you want to use this command when you want to find the probability that the number of successes is exactly equal to some number, okay, whatever the last number is you're doing here. When you want to add things up, then there's another command for that, and I will get to that in the next lesson. So go ahead, get some practice, and I'll see you next time.